Cool. Well, we'll go ahead and jump into it. Hey, everybody. My name is Scott Andreas. It's great to see all of you here in Denver at Community Over Code. Paulo, is the recording ready? Yep. Okay, cool. Hi, everybody. It's great to see all of you here in Denver at Community Over Code. My name is Scott Andreas. I'm an engineering manager at Apple, leading our work on the Apache Cassandra database process, as well as a PMC member and a committer on the Apache Cassandra project. The title of this presentation is Begin Transaction, Rethinking Apache Cassandra as a Transactional Database. While the title is transaction focused, this talk is really about telling the story of some very low-level changes that have been in progress in the Apache Cassandra project for the past couple of years, and how they fit together into something that's much larger than the sum of their individual parts that will shape the future of the database. The features you'll see represent a huge body of work. Cassandra contributors from a bunch of different companies and organizations and independent folks have been working on terraforming the database to bring industry-leading features to Apache Cassandra's users for a long time. And we're on the cusp of seeing some of that work come to life now. So my gratitude is with everyone who's contributed to making these features better, inclusive of CEP feedback, mailing list discussions, direct code contributions, documentation, just offhand comments. Thank you all very much for that work. So let's start by looking into, for an outline today, we're going to cover Apache Cassandra today, then cover some transactional capabilities that are coming in Apache Cassandra. We'll look at a demo application that highlights what you can build with these features, and then we'll talk about some future directions. So let's start by looking at some of the limitations in Cassandra as of today. Some of these are pretty severe. You've probably run into some of them yourselves. Others of you might have put them out of your mind or tried to forget. But most of what we'll see are pretty embarrassing for a database of our stature. Because you're about to see a feature checklist, and this is the beginning of the presentation, you might expect a lot of X's. So let's see what we've got. Has anybody here ever encountered schema disagreement in a live cluster before? Like, how do you even get out of that safely and properly? There's really not a good path. Because of that, there are a lot of folks who don't recommend that developers using Apache Cassandra target migration scripts like Liquibase, which create tables and modify DDL programmatically because of the potential for creating schema disagreements. And if people have to manage DDL by hand, that doesn't really feel like a great way to manage a distributed database. It's also not especially safe to drop and recreate a table in Apache Cassandra today. You sort of have two bad choices between using deterministic table IDs and not being able to safely drop and recreate a table without ensuring that all on-disk state has been purged, or using non-deterministic IDs and risking data being duplicated across different tables or not being inserted where you expect and becoming inaccessible. You also can't transact across partitions or across tables in Apache Cassandra today. This is something that's been possible in most relational databases since the 1970s. Cassandra does support lightweight transactions over a single partition, but they're not especially fast. In fact, right now in Paxos v1, transacting across regions requires 4 round trips on write. Paxos v2 improved that quite a lot to 2 round trips on write. But there's not an implementation in Cassandra today that gets you a transactional write or a transactional read guaranteed in 1 round trip. Cassandra also doesn't support referential integrity. So if you have data that's stored across multiple tables in the database, there's no way to enforce a referential integrity or foreign key constraint via a transactional mechanism in Cassandra. And our secondary indexes aren't quite yet feature rich, or at least before SAI landed. So there's not really a great way to define an index on a column and perform prefix queries over SS table attached data structures prior to SAI landing. So when you look at this, there are a lot of reasons why people have thought of Apache Cassandra as a database that's really hard to use, and that's mostly because it is. So we wanted to start solving these problems and think through how we could make Cassandra a better database. We certainly had a lot of work to do. And that work started at a pretty foundational level. It began with work on transactional metadata. Transactional metadata and distributed transactions are both on the order of 100,000 lines of code each, and SAI on the order of tens of thousands, inclusive of tests. All of these are major efforts and not just typing. Like, it's critical thought work and architecture required to get complex transactional protocols right. So this work starts with transactional metadata. When Cassandra was introduced 16 years ago, we used Gossip for broadcasting state. But building correct transactional systems on top of Gossip is nearly impossible. Gossip can't provide an ordered log or enable implementation of a safe state machine that allows for transitions from one state to the next. With Gossip, one node would effectively declare an action and then begin probabilistically broadcasting it to peers who would then do the same and others the same again until probably, definitely, maybe everybody got the message. So upon receiving a message, then nodes would take a compensating action like updating their local view of the ring and begin behaving accordingly. But that was incredibly unsafe too. So imagine the topology change that resulted in a period where coordinators and replicas might have disagreed on who owned what data. Reads could be misrouted, and writes could too, which could result in transient periods of writes landing on nodes that no longer own data, or reads hitting replicas that no longer contain it. This behavior is improved in the very most recent releases of 4x and 5x via out-of-token range blocking, but it's an example of the type of horrific behavior that can only be plastered over into a wholesale replacement with the transactional protocol. What you really need for cluster membership is something like a serializable log and a protocol that ensures all replicas advance together. Transactional metadata replaces gossip with Paxos. So changes to cluster state are now serialized by a Paxos query that's elected among the nodes in the cluster called the cluster metadata service. The cluster metadata service increments an epoch value as changes are made to cluster state. And if coordinators and replicas notice they disagree about an epoch, they catch each other up to ensure that they're responding to requests correctly. The underlying Paxos implementation is Paxos v2, which is roughly twice as fast as the original LWT implementation that shipped in Cassandra years ago. And you can learn more about transactional metadata in CEP 21. The cool thing about replacing gossip with serialized log is that it makes schema changes fast and transactional. It makes membership changes like expanding and shrinking clusters easier. And it makes range ownership changes in the database transactional and safe in ways that gossip never could. So I think of this work as foundational to the future architecture of Cassandra, even though it's not something that sounds like a very flashy feature from its name alone. The next major feature we're going to talk about today is distributed transactions. Distributed transactions enable Cassandra to achieve strict serializable isolation, the strongest ANSI isolation level that's possible for an ACID database. Distributed transactions solve the single partition transaction limit in Cassandra. They enable users to define many tables and to transact across them. This avoids the need to create awful contorted data models that don't match the user data that they store if you try to cram everything into a single partition and then make a key value data model that lets you transact across that. They also provide the foundation for future features that can be built on top of them, like record versioning. So Cassandra's upcoming implementation of distributed transactions is also leaderless. Like the database itself, this means that in multi-region topologies, you can initiate a transaction from any region without it first having to be forwarded to a designated proposer or primary region. And because it's leaderless, that means there's no single instance to bottleneck throughput. That might perform well in a single 3-node cluster, but would fall on its face at 1,000 nodes if you had all of the transaction volume passing through a single designated leader. Some people ask, why not Raft? Those are two of the primary reasons. So with transactional metadata complete and distributed transactions wrapping up, this brings us to the level where we'd rather be spending all of our time building rich features for users. These two layers bring us to what we've really been here for. Storage attached indexes is a really great example of this. So SAI for short originally developed a DataStax and then brought to the Apache Cassandra project as a community effort, is a local secondary index implementation that's safe and designed to scale for your largest applications. There are a lot of other features that can be built on the foundation of transactional metadata and distributed transactions. Some of them, like materialized views, can even be built today or be built in the sub-15 accord branch via users today in CQL. So in the spirit of showing, not telling, what I'd like to show you today is an example of an application you can build in Cassandra with these features. We're going to build a database that acts like a toy file system. So if you were building an app in traditional SQL, you might want to model it as having 3 tables: users, folders, and files. So as a feature, you might want to allow a user to arrange files in folders and to search folders by file type. You might want to have some constraints defined such that all files must belong to a user and to a folder, and that all folders need to belong to a user. And you arrive at the type of table that you would model if you were building this in Postgres or MySQL, for example. So let's move on to the demo. Sounds recorded. What I'm going to do is I'll launch CQLSH against a live deployed cluster and connect to the cluster. You can see it's running from the CEP 15 accord branch, Cassandra 5.1.0. We'll create a key space called demo first, with network topology strategy and one data center that has 3 replicas. Then we'll start building out our tables here. We'll create tables for user accounts, folders, and files. Our first table is the users table. And you'll see something new here. We're declaring a transactional mode called full as a table property. Next, we'll create a table called folders, again with transactional mode full. And now a new table called files, also with transactional mode full. These 3 represent the data model of our application. So from here, we're also going to create a new index using SAI or storage attached indexes that indexes our files on the file type column, which would make it possible for a user to query their files by file type. Now we're going to insert some data. We'll start by creating a user account. And because it's not appropriate for a user to launch an application or to log in after creating an account to find nothing there, we want to pre-populate it with some starting data. But the first thing that we do when we create a new user is to make sure that a user doesn't already exist with that same ID. So we have a let statement here that lets us find the result of a select to a variable called existing user. We'll test this variable in our transaction. So we say, if existing user is null, then. And then this is where we'll do our insert, only if there's no user with that primary key already. So we'll insert our user with my name and info. We'll create a new folder called home. And then we'll add a file to their folder called readme that just contains the text welcome. We then type endif to represent the end of the conditional block for our transaction. And then commit transaction, which commits our transaction as an atomic unit to the database, and it's been committed. So let's take a look at what we got. We'll do a quick select from users. You'll see what you expect. We've got one user entry. We've got one folder entry with the home folder. And we've got one file entry here. But all of these were inserted atomically. So if you were to have, let's say, 1,000 queries a second executing as that transaction executed in the transactional mode, only the final one would observe all of them present together atomically, rather than splayed results across the tables. So now we're going to insert files of a few different types and assert the valid account and a target folder too. So we start with begin transaction, and then we bind our valid user to the results of a select query for my ID. And then if we're going to add files to a folder, we should make sure that folder exists too, so we don't create dangling references. So we then search for an existing folder. Then we test for this, saying if the valid user is not null and the existing folder is not null, we're good. We can proceed with our insert into the files table and add a new file called test, again with welcome text, sure. We'll add one more file in here too. We'll just call this one a photo and give it an extension of type JPEG. Probably wouldn't want to use Cassandra to store raw files. So endif and then commit transaction to commit our write with these two new files that we've asserted are belonging to a valid user and an existing folder. We'll do a quick query just to show that all of them are there as we expect. And now let's test our property that lets users search for these files by type using the storage attached index that we've defined. So we'll select star from demo.files to show all of our text files. And we'll do one that shows all of our JPEGs. One thing you'll see here is that this query is still against the base table, demo.files. As a user, you don't have to specify a specific index that you're querying from. The database will use the SAI index for you. So let's say our user's not very happy. They tried out the product and thought, not for me. They want to atomically delete all of their files and folders. So we can type begin transaction and then delete from users, folders, and files with my ID, commit transaction, and we have atomically deleted all of the data for this account, ensuring referential integrity across all of the tables that are involved. And if we do quick selects, we'll of course see that all of those are empty as well. So I hope for most, this feels a lot more like building a normal application and starts to sort of unwarp our minds from some of the ways that we've been having to model things in Cassandra for a really long time. Let's take a quick look at a recap of what we saw here. So we demonstrated multi-table transactions. These enable ACID transactions across tables so users can define schemas that make sense and use Cassandra more like a relational database. We saw strict serializable reads, the strongest level of isolation possible. We demonstrated how to enforce referential integrity across records, enabling Cassandra to do the hard work of avoiding race conditions in data instead of forcing applications to figure out how to do that. And we saw transactional DDL, create table statements, which are guaranteed to converge and linearize, enabling users to manage schema programmatically with tools like Liquibase as well. So we'll now take a short tour behind the scenes on what happened as we executed these queries. It's probably obvious that this wasn't easy and that this takes a lot of work. Here's a 10-second clip of a debugging tool that Alex Petrov developed for tracing the execution of a transaction throughout the distributed system. This message flow diagram that covers both the distributed protocol and local reads has been super handy for visualizing transaction execution inside the database and debugging some aspects of the feature. Back to a higher level. So one of the concepts you see here is enforcing referential integrity in the database. This brings a core relational feature to Cassandra. Cassandra's never been able to do this before. Distributed transactions enable users to enforce constraints and relationships across tables in Cassandra. So as an example, one of the queries you saw adds new files to the database. That query asserts that a matching user exists when data is inserted, and that the folder they're inserting data into exists too, despite inserting only data into the files table. This helps app developers avoid critical race conditions, preventing dangling files that don't belong to a folder or inserting data for a user that doesn't exist. Distributed transactions today enable you to manually enforce referential integrity in a query. But you could imagine a future version where syntactic sugar in the table's DDL enables this to be enforced by the database automatically. We could even enable declaring something as formal as a foreign key relationship as a property of the table, which is something that might follow someday. Now, let's take a look behind the scenes at what happens while we execute the DDL statements that created and dropped these tables. Transactional metadata advances user state in epochs. It ensures that all replicas agree on cluster configuration when serving a request, so the database advances perfectly in sync. This works by passing all changes through a serialized log and incrementing this epoch value that you see here at right. Each time you make a change to cluster state, such as joining a node, decommissioning a node, or changing schema, that epoch value will increment. Epochs ensure that all replicas agree on cluster configuration when serving a request, and all changes to cluster configuration are passed through a serialized log that increments this as they go. So epochs enable safe and rapid changes to cluster state via Paxos. The other thing to remember is that transactional DDL is safer DDL. Under transactional metadata, since all key spaces and tables are versioned by epoch, this means several things. The first is that it's now impossible for schema conflicts to emerge within a cluster. It's also impossible for duplicate table IDs to emerge from the same create table statement if you use non-deterministic IDs. And if you use deterministic IDs for your tables, the epoch of when they were created and dropped or truncated is preserved, which means that the state machine of managing these tables and the underlying files on disk is now perfectly safe where it wasn't before. So now let's talk a little more about transacting across tables and partitions. Distributed transactions make data modeling for your application much simpler. They let you think in terms of the app your data handles instead of spending all your time building complex, brittle, and application-level state machines that try to compensate for Cassandra's inability to perform atomic transactions. Think back to the simplicity of what SQL promised for managing data when you first used a database like Postgres or MySQL or SQL Server. That's a lot closer to what we have in mind. So transactions make building applications on Cassandra safer and easier. You don't need a PhD in consistency levels and CRDTs to build the equivalent of a Rails app from 2008 anymore. I'd like to zoom out a bit from the protocol to think about the impact this work can have on Apache Cassandra as a petabyte-scale database in relationship to the wider field. With this work, Cassandra will become the only distributed database in the industry that can scale to petabytes of data, offer strict serializable isolation, be deployed in any data center or any public cloud, to have the ability and performance advantages of a leaderless database, and single round-trip latency for transactions, whether on a single key or multiple, local or remote. This slide in this comparison matrix doesn't mean that Cassandra is the very best database for all applications, and there are other characteristics that you could optimize for that aren't captured here. But this set of capabilities is incredibly compelling and something that we weren't entirely sure would have been possible at the outset. Next, I'd like to add a bit on the index implementation that you saw in the demo. Storage-attached indexes were implemented as part of CEP 7 and released in Cassandra 5.0, which has a super elaborate design doc on ASF Confluence if you're curious. SAI is unique as an index implementation in that the index is implemented as an SS table component, meaning that the index pointers draw SS table data, and the SS table data themselves are co-located inside the SS table components. This also means that SAI is at its very best when it's used as a partition-restricted index rather than a global index. So if you can design your data model to ensure that you're indexing and querying within a partition, this completely eliminates the scatter-gather behavior of legacy indexes and enables index queries to hit a single replica set and respond rapidly. If you need a global index, one of the best ways to achieve this soon might be to materialize it via a distributed transaction directly in a derived table, which enables you to transactionally mutate data in a primary table and a materialized index together. Again, you can imagine future work that enables this to become syntactic sugar that's managed by the underlying transaction protocol itself. I'm kind of talking out of both sides of my mouth when I'm saying that there are new features that are coming and that it's impossible to manage this directly right now, but you can do so with a distributed transaction. But the real point is that things that were impossible are becoming possible, and soon we can take those things that are possible and make them easy. So back to 1 year ago. At that time, none of this was possible in Cassandra. The database had some pretty severe limitations, and it was so difficult to use that folks had resorted to pretty serious games of Twister to achieve their goals in Cassandra. This year, Apache Cassandra is beginning to turn these X's into checkmarks. And I'm so proud that the project is delivering capabilities needed to implement programmatic DDL and the ability to drop tables and recreate them safely, transact across partitions and tables, cut transactional latency in half, provide a path to referential integrity, and shipping a great secondary index implementation for users. So next, I'd like to offer a quick peek behind the scenes on the transactional protocol that makes this possible. This is a protocol called Accord. It's a Paxos-based distributed transaction protocol related to ePaxos that operates based on participants proposing a key set and a logical timestamp to all of the replicas that participate in quorums from the key set. The name is sort of a play on words. The original Paxos paper was called the Part-Time Parliament. What we're sort of envisioning here is consensus across parliaments or an accord in which those parliaments can reach agreement across each other. Accord enables leaderless transactions to be implemented from any region. So if you run clusters that span multiple data centers, you can run active-active without transactions having to be forwarded to a primary. These also execute in a single round trip in the common case with a comparatively rare fallback to 3 round trips in cases where conflicting dependency sets have observed a logical timestamp that's greater than the proposal. One of the raft criticisms of Paxos as a protocol is that Paxos isn't as easy to learn or teach, and I don't entirely disagree with that. But it does enable us to achieve properties that are superior to raft through hard work that's been validated by a formal proof, research collaboration, and exhaustive simulation. So there's a property that you saw in the demo that's new on tables called transactional mode equals something. What does it mean for a table to be transactional? There are a few transactional modes that you should know about. The first is off. So this is effectively the same as what you have today in Cassandra. Distributed transactions via Accord are disabled. Paxos v1 and Paxos v2 are supported. The second is unsafe. This permits writes via the standard storage proxy write path. So if you're mixing writes that are unsafe by the normal consistency levels in Accord transactions, this could result in the Accord protocol computing multiple outcomes for transactions depending on data written by non-serial writes. You shouldn't use this. In the spirit of always making sure that users are in control of their clusters and their configuration, these modes are provided in case someone has some very particular need or believes that it's necessary and right. But I wouldn't use unsafe. From here, though, we're in a world where people might get more creative and have bright ideas about how to use Cassandra differently. Unsafe writes is a mode that allows non-serial writes, but still forces blocking read repair via the Accord protocol. So this means that it's safe to perform non-serial reads of data that's written by Accord, but it's not safe to write data at a non-transactional consistency level that Accord might read. So if you want to issue transactional writes and allow for non-transactional reads, you can do something like this. Next, mixed reads is a mode that executes all writes via Accord, and then commits are performed at the provided consistency level to enable data to be read via non-serial reads. This means that it's safe to read or write data that Accord will write. And the final mode is full. This one is simple. It provides full serializable semantics for all queries. Consistency levels do not apply. This is a new interesting world for Cassandra. Ariel Weisberg in particular has put in a ton of work to think about the interoperability of Accord's transactional modes with non-transactional consistency levels. So if you have any questions, you should reach out to him. He's here in the room today too. Now let's talk a little more about the transaction syntax. Since we've got an understanding of the semantics and the decent background on the secret menu of transaction modes, I hope that left you on the last slide thinking in full is a pretty good place to be, or at least a very good place to start, with some options to look back at if an unusual situation arises. So let's take a closer look at the transaction syntax. Every transaction begins with a begin transaction block. Then one or more let statements allow you to bind the result of a select statement to a variable that can be referenced within the scope of the transaction. Following this, a select statement defines what's to be returned from the transaction, referencing the state prior to the transaction's execution. Then comes the predicate, an if statement that allows you to test conditions that determine whether or not mutations should apply. This is similar to the if clause in LWTs today. And then end if concludes the predicate. Finally, commit transaction concludes the transaction block, indicating that the transaction is complete, well-formed, and ready to be executed. All of this executes as a single atomic unit, so it's a little different from databases like Postgres, where you can enter a transaction scope and then execute interactive queries. Instead, you're submitting all of this to be executed as a batch. Next, I'd like to talk about how distributed transactions are composable with more conventional Cassandra features like SAI. Transactions aren't designed to be implemented as an exotic subsystem or require extensive work to make interoperable with other features. We'd like to think of these in layers. We want them to just work too, and with the new SAI index implementation, they do. This means that if you have a table that declares transactional mode full, all reads and writes pass through the transactional subsystem, including for your storage attached indexes. The ACID transactional guarantees of the port also apply to secondary indexes fully. So on the write path, transactions update the index and guarantee isolation and atomic visibility to future transactional reads. And on the read path, the transactional protocol ensures that execution happens after all transactions with conflicting dependencies have committed as well. So you can trust that work with storage attached indexes will compose well with the port. Materialized views are another example, and an interesting part of Cassandra's history. The implementation in Cassandra today is unsafe and was retroactively classified as experimental to reflect this. The materialized views that exist today can become unrecoverably out of sync with no mechanism to bring back into sync aside from recreating them. So here's an example of a transaction that implements materialized views. Let's say we wanted to be able to look up user files by their hash value in our toy application. So in this example, we have our standard files table, and we've added a new one here called files hashed. We maintain both of our base files table and our derived files hash table by performing the insert to both in a transaction that guarantees the state of both tables will advance together, fully respecting Cassandra's ACID properties. It's true that this would be a manually maintained materialized view, and that I'm falling back again on making users do the work in Cassandra. But you could imagine a future implementation of materialized views that implements this as part of the database's transaction subsystem automatically as syntactic sugar, and doesn't require you to manually maintain a derived table like this. Start by making things possible, and then we'll try to make things even easier. So there's even more that we can do with this. Where do we go from here? One thing we know we need to improve is the ergonomics of determining whether or not a transaction has been applied. So today, the best way to do this is to get the information by selecting the condition you test to be returned as a response to your query. Future changes to the wire protocol can improve how we communicate this, but will require revving a major version, and it's something we should probably talk about as a development community. One feature I'd love to add also requires wire protocol and client and driver revisions is multi-result select statements. This would enable you to return multiple result sets from a transaction, but it requires changes to the clients and drivers. One of our design goals in the initial work here was to ensure that all clients and drivers that exist today already work with the feature, so people adopting the feature don't have to go around upgrading for every one of their applications. Strict serializable snapshots are another feature that become possible too. By implementing an exclusive sync point, you could imagine enhancing Cassandra to execute a strict serializable snapshot that represents the transactionally consistent state of the database across all tables in logical time. So a full ACID snapshot of the database would be a huge improvement over today's snapshots, which cannot provide ACID properties and which might also exhibit serious time splay across nodes depending on when a snapshot was requested and when it was executed on each local instance. Snapshot isolation is another possibility. So adding a concept of record versioning and pruning may enable us to support proper MVCC in Cassandra. This would also enable paging over transactionally consistent result sets. So you might have had someone ask you what happens if the underlying data changes while they're paging over a result set in Cassandra. Snapshot isolation would solve that problem. We could add foreign key constraints too. So the demo you saw implemented something like foreign key constraints in CQL. But we could push this capability down to the database itself and enable Cassandra to enforce referential integrity across tables for us. This would bring referential integrity constraints into the database schema natively. All right, so you've been hearing about Accord for a while, and not just this year. What's going on with it? You can follow all of this work on the Apache Cassandra Jira, and also on the project's GitHub branch at CEP15 Accord, with the URL here on the slide too. There's also a lot that's wrapped up recently that I'd love to share with you too. One of the largest components of the projects that recently wrapped is Accord's journal, which is an addressable write-ahead log for transactions that provides durability across process restarts. We also have some work ahead on testing and validation of the implementation. So all the work on the protocol is involved in incremental testing and validation. We'll be advancing to larger scale simulation of that implementation once some of the dust is settled. We know we've got some perf work ahead too. The baseline target is for queries to be as inexpensive as Paxos v2 to execute, but with half the round trips. And in terms of merge timeline, I'm really hopeful that this work will be set to merge to trunk within a month or two. Project contributors have started a thread on the mailing list to solicit review participation and feedback. So if you're interested in taking a look at the work, we'd love for you to get involved. And if you'd like to try it out, you can just clone that branch and run M artifacts. John had also mentioned yesterday that he might be adding support to EasyCast Lab to build and test clusters from that branch to make testing deployed versions easier too. With that, I'm happy to answer any questions and heckling and corrections from the Accord project team for any errors and omissions here, with the help of the few folks in the room who've done a lot of the real work on this. Thanks, everybody. Yeah, Jordan.
You have the slide of like the different modes. You know,
Yeah.
So I was in the off mode, I think it's just called.
Yeah.
So do I just get in off mode like Cassandra today plus TCM?
Yeah, exactly. So if you use the begin transaction syntax, the query would just be invalid.
Okay. So you can still like operate if I want to leave your local table by table.
Absolutely, yeah. There's also a YAML property that enables the Accord transaction protocol too. So this is also guarded behind that to prevent potential users from creating tables using a transaction protocol you're not ready to call gold yet.
And then what was the reason for the middle three modes? Like I definitely get it off and full, but like in what world would I ever want one? Like why does the unsafe ones even exist?
That's a very neat question. The unsafe ones, I actually looked to remove before, because no one asked for them. They don't. You can always add them later, sort of thing. So mixed reads is they basically if you're not getting the performance or throughput you want out of the core. Remember, this stuff was done concurrently with the core. We didn't know where we were going to end up performance-wise, so like you wanted to have the option of, well, okay, what if you ran part of the workload non-transactionally for throughput or latency?
For the read,
some of it,
the read.
Yeah, maybe the read part, maybe the write part, just depends. And then you can just do transactions on the data you want to handle transactions tables. But really, like, if you want to do non-transaction stuff, do it in a different table.
Yeah. So like mixed reads would kind of give you like with that CD or forgetting the other one right now that's perhaps, but like where you can like read stale data from replicas kind of thing instead of like funneling your reads
like
through the
read.
Sorry.
So if you did a non-transactional read in mixed reads, it would be like probably read. You would read anything that ain't committed before transaction. So Accord does synchronous commit.
Yeah. Okay, that's you're gonna see a valid data, but you're not necessarily gonna see the most recent, right?
Yeah.
Okay.
Yeah, you won't necessarily see that because the Accord. Well, no. You will see the most recent acknowledged right from the Accord will apply. So it's not. Yeah.
Okay.
Yeah, we're really hoping that most people. We're really hoping that most people will think about defaulting to full and hanging out here as the baseline. I know that everybody in Cassandra loves thinking about consistency levels and overlapping forums, but
feedback. Like, let's please rip out the middle three, or at least the ones that start with unsafe.
So part of the goal was to make it possible to drop it forward over Paxos, including doing things you should do in Paxos. So
yeah, the reason mixed reads exists is because it actually happens when you migrate to full. The period in between while it's migrating is mixed reads.
No, I get mixed reads. I should rephrase my feedback would be let's remove the unsafe ones and let's remember unsafe assassinate endpoint.
that's good feedback.
which was the best main feature in Cassandra.
I love telling people who don't have Cassandra background, yeah, just go run unsafe assassinate endpoint. And that's like to put purpose on my feedback, trying to explain to like my internal engineers why I have set unsafe rights or why it exists.
Yep.
We are not two circles, so
Yeah, but yeah, I definitely understand why mixed reads exist, and I think like that mode. Technically, when you use LWTs today, and people like a lot of people use LWTs on writes and then use local quorum on reads, you're kind of getting mixed read mode today.
Francisco, then Paolo?
Okay, I was wondering what's the default mode for transactional?
It has to be specified in the DDL syntax here. Actually, is that the case? Like,
It's off.
off. Okay.
It's off by default. There is a config that you can change the cluster default to whatever you want, but the default out of the box.
So the current recommendation, if you want like very high throughput, is to avoid operations across multiple partitions, like batches or in clauses, because of the load it puts on the coordinator. Will Accord change this, or is still it's recommended to avoid if you really want high throughput and you don't care a lot about consistency?
Sure. If you really want high throughput and don't care a lot about consistency, then you might not need a transactional mode. What you're doing with Cassandra today might make more sense. If you do care about transactional semantics, we want to make sure that it's first correct according to the asset properties, and then second as fast as it can possibly be. Some testing that we'll have ahead of us is to figure out like how large the key set can or should be across tables for this to perform really well. Like, you could imagine users performing 15-way transactions that involve every single node in the cluster. Those would certainly require more effort for the database than those that just touch a single partition. But there's some future perf work ahead to, I think, figure that out. But wanted to start by making the feature possible and correct, and then fast, and figure out what type of guardrails you could put around it.
So one piece of information I want to volunteer about performance is that Accord does gain performance advantages. So we don't know where we're going to end up. So for example, Accord only needs to read from one replica. So like if your reads are expensive, Accord actually wins resources in that area.
That's a great point. Yeah, for those who might not have been able to hear Ariel's point, is that Accord is able to read from just a single replica, which means that if you're doing a local quorum read that would ordinarily touch at minimum 2 replicas, you're actually hitting disk half the time. Caleb?
Yeah, and if you think about what kind of reads are expensive, like local secondary index reads are usually one of those. So Accord makes SAI faster.
So it's a single replica in all cases? What do you pay for that?
Nothing.
It's all,
So that's what
operations
doing the transactional metadata. That's how you, instead of doing a data read, you look at the transactional metadata, not the cluster transaction, but the metadata for the transactions. And so then you know if the data that you're reading is fresh.
And when it's not fresh.
It's not able to execute. So everything is serializable. So you can't, the local node will not be able to do the read. So we'll have to call back to that.
So that's the cost of the read latency.
Which is just fall back. Is we fall back and we add time out of effect. So if you do hit a node that is, if you choose a node that is out of sync, we then fall back to another.
You have applied dependencies.
Yeah, if you can do the read locally because you're up to date, which is the common case. You can do the read. If for whatever reason you're not.
But that's what made the writes go from, like, because in the local quorum case, that's true on the reads, but on the writes, my writes are now all order of WT instead of order of, okay. So the cost is the writes and the staleness.
And if you're not correct, I think it sends a message back to the coordinator immediately, right?
Yes.
So it can immediately go find another replica, and it can pick replicas from a local data set. So if you're optimizing for multi-DC, you're not increasing the number of landmines.
And then my actual question before we get on the topic was, when you're in off, is the code the same as like Cassandra 4.1? Like, am I using the same subsystem at that point?
Yeah.
And have we benchmarked that like that?
The benchmarking is in progress now. Okay. Yeah, so the existing subsystem could be Paxos v1 or Paxos v2, depending on what you configured for the database.
Well, I'm hearing more than like my local quorum reads and writes. So
Oh yeah, no change at all there.
okay. So it's just like if off, hold that.
Yeah, you're just a storage proxy.
Okay.
Cool. Any other questions? Patrick?
I didn't quite catch, is that transactional mode required, or is there a default as well?
The default's off,
Okay.
and then if you enable it, you're effectively enabling Accord by selecting into one of those transaction modes.
So if I have existing schema, then I will have to do an alter table to do transactions on those?
That's right.
Okay.
At this time, yes. Abe?
For users that are burned by LWTs, not directly from latency, but from contention, how will those users experience Accord differently?
That's a fantastic question. Thank you for asking. So today in LWTs, you effectively have multiple nodes that could be committing or contending on the same key, and then they'll enter this backup loop, and you get cast write timeouts and an indeterminate outcome. That changes in Accord because what Accord is effectively doing is allowing the nodes to agree on a logical execution timestamp for the transaction, which is effectively always going to succeed. All you're just trying to do is to get a higher timestamp. And then at that point, you test the conditions in your transaction. So the behavior that you might see if you have a very high rate of contention could be for those conditions not to test, or for you to have false evaluations of those. in the event that competing transactions have issued writes that now make those conflict. But as a user, you would effectively always see the system advancing in state rather than hitting cast write timeouts in determined states. In the back?
Yeah, is there support for multiple predicates, and if not, any thoughts on that?
So we do support, let's see if I have an example ahead here. Testing multiple conditions together. Can you say more about what you mean by multiple predicates? If it's
more like multiple if statements instead of just like one logical
Oh.
statement that's checked and you apply it.
Yes, I see. So conditional on this, you might want to conditionally insert or not insert data into a table.
If this Boolean statement is bad, apply these, but if this one is bad, apply these.
Like do that.
Yeah. Adina?
Oh, yeah, not yet.
Okay.
Yeah, but a great concept and one that I think would be feasible to implement and test as part of something like this.
It's interesting if they're conflicting statements, like if two of them are true, what do you do?
Right.
Both, or you say it's wrong?
Jordan?
Just a follow-up to Dave's question. Does it use internal tables in any of those? And the reason I ask is we've recently found that you can introduce contention into the LWT system with no contention. So I had a customer who puts a lock in front of their LWTs, and yet we see these massive spikes in contention, and they are usually days. No, but there's contention here. And what we actually found out was that the amount of writes to the Paxos internal table leads to backups in the mem tables being flushed. That leads to what appears in the subsystem to be contention when there is no contention. And so I'm curious if that failure mode can exist in the core using internal tables.
Alex can cover that one. And then I think we're at
Dave's shaking his head, so I'm assuming.
No.
So no, it's not using, like it doesn't have a.
We do use internal tables, but not on the plug path. We use it for hashes, for master keys.
Okay, so it's not like system.paxos.
No.
Okay, because that's what you'll see is you'll see
Yeah.
the flushing on system.paxos.
Yeah, we have a separate like commit log, a journal,
Okay.
which is being used for like sort of like durability,
So
and
perfect.
that's the only point of contention with the rest of the system. And you can probably speak better about like master keys tables. I don't think that there is any contention of those, right? Because they're flushed only on the like division.
Yeah. Okay. So that sounds like kind of, that's awesome. That was a fun new thought.
Cool. Well, thanks everybody. With that, we're at time. I really appreciate all of you joining today, and my congratulations and thanks to everyone on the distributed transactions, transactional metadata, SAI project teams, and everyone who's contributed to those and provided feedback. Folks who work on all of these are here today, so if you have questions about them, come find us and ask. More than happy to talk more outside the session too. Thanks.